However, before we begin, we must address the greatest law in the Bohr Planetary Model for hydrogen, and that is that atomic hydrogen does not exist. Ask anyone for a container of atomic hydrogen, and they'll give you a container of molecular hydrogen. Now I can, and in a future video I will, do a four-body analysis of the hydrogen molecule. But for this proof of concept, I'll do a three-body analysis of atomic helium. Since the helium nucleus is over 7,000 times more massive than each electron, it will be considered a fixed point. Further, if we assume that each electron will be in the other's Lagrange L3 point, then the only one set of equations will be necessary, since the equations of one electron can be applied to the other. For this proof of concept, I'm not concerned with the actual values, just the comparisons. Therefore, I assign the value of 1 to all constant. Coulomb's constant equals 1, charge of nucleus plus 2, charge of each electron minus 1, and a Bohr radius of 1. The force of charge of the proton on the electron will be a plus 2 attractive force. The force of charge on the opposite electron on the other will be minus 1/4, a repulsive charge. The net charge will be 1.75 positive, attractive, and perpendicular to the motion of electrons, assuming instantaneous velocity of charge. However, LIGO-Virgo have determined that the effects of gravity travel at the maximum speed of light. It is also known that electricity is not instantaneous. So the assumption that charge and magnetism travel at the maximum speed of light is a logical extension. Therefore, by the time the effects of charge from one electron reaches the other, they have both moved. Each electron perceives the other not where it is, but where it was. So while the attractive charge of the nucleus remains perpendicular to the velocity, the repulsive charge of the electron is obtuse, making the net force acting on each electron also slightly obtuse, causing each electron to slowly spiral outward. Now with LIGO-Virgo, the angle was acute, so that the masses spiraled inward. The kinetic energy gained was less than the potential energy lost, resulting in a net energy loss. This reduced the theory of the law of conservation of energy from an absolute to a good estimate when the velocities were slow. Likewise, as the electron spiraled outward, the potential energy gained is greater than the kinetic energy loss, resulting in a net energy gain. We have now demonstrated the source of energy on the electron for the electrons to be able to produce a magnetic field. While the net charge force is dependent on the inverse square of the radius, the net charge expansion force is dependent on the small angle above 90 degrees, which is proportional to the velocity. Therefore, the next charge expansion force is proportional to the velocity divided by the radius squared. The magnetic decay experienced is dependent on the frequency. Therefore, the net magnetic decay force is proportional to the velocity divided by the radius. Since we're doing a comparison of expansion versus decay, at any given instant, the velocities would be the same, so it can be removed from the comparison. The following chart is a comparison of the forces of net charge expansion versus magnetic decay at different radii, where the charge of expansion is proportional to the inverse of the radius squared, while magnetic decay is proportional to the inverse of the radius. At a Bohr radius of 1, the force of charge expansion equals the force of magnetic decay, and the orbits are stable. At half the Bohr radius, the force of charge expansion, which is 4, is greater than the force of magnetic decay, which is 2, and the orbits spiral outward. At twice the Bohr radius, the force of charge expansion, which is 1/4, is less than the force of magnetic decay, which is 1/2, and the orbits spiral inward. By applying the maximum speed of light to the velocities of charge, we just resolved two of the three major issues plaguing the Bohr Planetary Model: the source of energy required to produce a magnetic field, and why all helium atoms have the same radii. The next thing to address is the orbital plane. I'm going to assume a constant radius and declare a time increment as the time it takes charge to cross the diameter of the helium atom. At time equals 0, both electrons are on the orbital plane, the dotted line. At time equals 1, I'm going to move electron B up 1 increment above the orbital plane, the dotted line, giving it a velocity of 0 and acceleration of 1 down. Electron B matches A at time equals 0, the green line. At time equals 2, A opposes B for time equals 1, orange. B moves down with velocity 1 and acceleration 0, green. At time equals 3, A opposes B for time equals 2, blue. B moves down with velocity 0 and acceleration 1 up, orange, causing the velocity to increase to 2 by increment 4. At time equals 5, acceleration has increased to 3, orange sees red, to 4 by increment 7, red sees orange. By this analysis, there are 400 increments per orbit. A proper one should have at least 3 increments per diameter, resulting in 1200 increments per orbit. But that won't be necessary, recognizing that with the constant pitching and yawing over time, the perceived orbital plane of the electrons would constantly change from the reference plane, resulting in what would appear randomized electron paths, fulfilling the Heisenberg uncertainty principle. Now, although I just demonstrated the unstable orbit plane, let's assume for a moment that the orbital plane and the orbital radius are both constant. If we accept Bohr orbital radius of 31 pentameters with a circumference of 2 pi r equal to 195 times 10 to the power of minus 12 meters, electron velocity of 2.19 times 10 to the power of 6 meters per second, or about 73% the maximum speed of light. This would give an orbital period of 89 atmoseconds. For perspective, less than half a microsecond, each electron will have orbited more times than the Earth has. At 1/1000th of a second, the maximum shutter speed of a typical film camera, each electron will have orbited 2.5 times that the Earth has. This means that the electron cloud is not a cloud, but 2 electron trails. These electron trails are not circular, but rather have a stable but fluctuating radius with completely unstable orbital plane. So it can be easily understood how these 2 electron trails could be confused for electron cloud. It would be similar as you looking back at your GPS record for the month, picking a location at random, and confidently stating that you spent the entire month at the Tim Hortons drive-thru 3 cars from the takeout window. The Schrödinger electron cloud and my electron trail would look very same from the outside. Electron cloud is like a solid sphere that is fuzzy on the surface. The electron trails is like a spherical shell that is fuzzy on both the outside and the inside. The magnetic fields of the electron, whose orbits are not identical, are originally used to increase the rotational inertia of the nucleus. However, because the orbital planes of electrons are constantly changing, the magnetic flux of the nucleus, which is perpendicular to this plane, is also constantly changing. This energy is used to constantly change the axis of rotation of the nucleus to align with this previous orientation, and with the delayed magnetic field of the rotating nucleus, which is aligned with the obsolete magnetic flux, offers a counter EMF for the orbiting electrons, causing them to continually lose energy. My name is Richard, and this is my defense for the support of the Bohr Planetary Model as applied to helium.